The PAPILLON system employs a modular DSPy program to balance privacy and quality by delegating tasks to an untrusted external LLM while preserving user data confidentiality. This architecture uses a local language model to craft privacy-preserving requests and generate responses, leveraging the external model's capabilities without exposing sensitive information. We will now examine how the PAPILLON system is initialized and optimized using the ArborGRPO compiler, which fine-tunes the local model's weights to maximize a composite metric that evaluates both response quality and privacy preservation. The configuration includes specific training parameters for multi-GPU training, LoRA adaptation, and reinforcement learning optimization. PAPILLON equals PAPILLON untrusted model equals OpenAI LM. PAPILLON set LM local LM. Hash note training on 4 GPUs. Train quarks equals per device train batch size 8. Gradient accumulation steps 4. Temperature 1. Top K -1. Top P 1. Repetition penalty 1. Beta 0. Learning rate 1e6. Gradient checkpointing true. BF16 true. LR scheduler type constant with warm-up. Loss type DAPO. Max steps 1000. Report to WANDB. Log completions true. Logging steps 1. Max prompt length none. Max completion length none. Scale rewards false. Max grad norm 1. LoRA config. LoRA alpha 16. LoRA dropout 0.05. R8. Target modules QProj, KProj, VProj, OProj, UpProj, DownProj, GateProj. Num training GPUS 3. Num inference GPUS 1. Weight decay 0.001. Compiler equals ArborGRPO. Metric equals compute overall score. Multitask equals true. Num DSPy examples per GRPO step equals 4. Num samples per input equals 8. Exclude demos equals true. Num train steps equals 500. Num threads equals 24. Use train as val equals false. Num steps for val equals 10. Train quarks equals train quarks. Report train scores equals false. Optimized PAPILLON equals compiler compile. Student equals PAPILLON. Train set equals train set. Val set equals dev set. This code demonstrates the optimization of a PAPILLON system using the ArborGRPO compiler, which is a generalization of the GRPO online RL algorithm for multi-module LM programs. The PAPILLON system is designed for privacy-preserving delegation, where a local model trusted but lower quality uses an external, untrusted but more powerful LLM to balance high-quality responses with user privacy. The optimization process begins by initializing the PAPILLON system with an untrusted model, OpenAI LM, and setting the local model, local LM, for inference. The train quarks dictionary configures the training process with parameters like batch size, learning rate, and LoRA, low-rank adaptation settings, which are crucial for efficient fine-tuning of the local model. The ArborGRPO compiler is then initialized with these training parameters, along with settings specific to the GRPO algorithm, such as the number of DSPy examples per step and the number of samples per input. The compiler is configured to maximize the compute overall score metric, which evaluates both the quality of responses and the leakage of private information. The compile method of the ArborGRPO compiler is called with the PAPILLON system, training set, and validation set to optimize the system. This process involves fine-tuning the local model's weights to improve its performance on the given task, while minimizing the leakage of private information to the untrusted model. The optimized PAPILLON system is then ready for use, with preliminary experiments showing a boost in the composite score from 54.6% to 60% after 3 hours of training on 4 GPUs. This approach is particularly useful for scenarios where privacy is a concern, and the local model needs to leverage external resources without compromising sensitive information. Let's break it down.
PAPILLON equals PAPILLON untrusted model equals OpenAI LM.
Creates a PAPILLON instance named PAPILLON configured with an untrusted OpenAI language model, OpenAI LM, as its external model component. This sets up a privacy-preserving framework where the local trusted model can leverage the more powerful but untrusted remote model while minimizing PII leakage.
PAPILLON set LM local LM.
Sets the language model for the PAPILLON system to use the specified local model. This configures the system to utilize the local model for subsequent operations.
Train quargs equals.
Initializes a dictionary named train quargs to store configuration parameters for training a DSPy program. This dictionary will likely contain key value pairs specifying training settings, such as the optimizer type, dataset references, or hyperparameters like batch size and learning rate. The empty curly braces indicate it's being created, but not yet populated with any specific training arguments.
Per device train batch size, 8.
Sets the batch size for training data per device to 8, controlling how many training examples are processed simultaneously on each GPU or accelerator during model training.
Gradient accumulation steps, 4.
Sets the number of gradient accumulation steps to 4, which means the optimizer will accumulate gradients over 4 batches before performing a weight update. This effectively increases the batch size by a factor of 4 without requiring more memory per batch, allowing for larger effective batch sizes during training.
Temperature, 1.
Sets the temperature parameter to 1, which controls the randomness of text generation in language models. A value of 1 means maximum randomness, producing more diverse and creative outputs.
Top K, -1.
Sets the top K parameter to -1, which typically indicates that all available results should be returned without limiting the number of top candidates. This is often used in retrieval or ranking scenarios where you want to consider the entire result set rather than a truncated subset.
Top P, 1.
Sets the top P parameter to 1, which controls nucleus sampling during text generation by selecting from the smallest set of tokens whose cumulative probability exceeds this threshold.
Repetition penalty, 1.
Sets the repetition penalty parameter to 1, which controls how strongly the language model should avoid repeating the same tokens or phrases in its output. A value of 1 means no penalty is applied, allowing the model to repeat tokens freely based on its natural generation behavior.
Beta, 0.
Sets the parameter beta to a floating point value of 0, likely configuring a hyperparameter for a DSPy optimizer or module where beta controls some aspect of the optimization process, such as exploration-exploitation trade-off or learning rate scaling.
Learning rate, 1e6.
Sets the learning rate to 1e60.0000001 for the optimization process, controlling the step size at which the optimizer updates model parameters during training.
Gradient checkpointing, true.
Enables gradient checkpointing to trade compute for memory efficiency during training. This technique recomputes intermediate activations during the backward pass instead of storing them, reducing memory usage at the cost of additional compute time.
BF16, true.
Sets the BF16 parameter to true, enabling 16-bit brain floating point precision for numerical operations in the context where this configuration is applied. This typically reduces memory usage and can accelerate computation on compatible hardware while maintaining precision suitable for many machine learning tasks.
LR scheduler type, constant with warm-up.
Sets the learning rate scheduler type to constant with warm-up, which maintains a constant learning rate after an initial warm-up period where the learning rate gradually increases.
Loss type, DAPO.
Sets the loss type to DAPO for the optimization process, specifying that the DAPO direct alignment preference optimization loss function will be used to guide the optimization of the DSPy program.
Max steps, 1000.
Sets the maximum number of optimization steps to 1000 for the DSPy optimizer, limiting how many iterations the optimization process will run before stopping.
Report to, WANDB.
Configures the DSPy system to report metrics and logs to weights and biases WANDB, enabling experiment tracking and visualization of optimization results.
Log completions, true.
Enables logging of completion outputs during DSPy program execution, storing the raw responses from language model calls for debugging and analysis purposes.
Logging steps, 1.
Sets the logging frequency to 1, meaning logs will be recorded at every training step during optimization.
Max prompt length, none.
Sets the maximum prompt length to unlimited by assigning none to the max prompt length parameter. This allows prompts to be of any length without truncation.
Max completion length, none.
Sets the maximum completion length to none, indicating no explicit limit on the length of generated text outputs. This allows the language model to produce responses of any length until it naturally stops or reaches system-imposed constraints.
Scale rewards, false.
Sets the scale rewards parameter to false, disabling any automatic scaling or normalization of reward values during optimization. This means rewards will be used in their raw, unmodified form when evaluating program performance.
Max grad norm, 1.
Sets the maximum gradient norm to 1 during optimization, which clips gradients to prevent exploding gradient problems and stabilize training.
LoRA alpha, 16.
Sets the LoRA low-rank adaptation alpha parameter to 16, controlling the scaling factor for the low-rank matrices during fine-tuning. This value balances the contribution of the adapted weights relative to the original model weights, with higher values increasing the influence of the fine-tuned adjustments.
LoRA dropout, 0.05.
Sets the LoRA low-rank adaptation dropout rate to 0.05, which controls the probability of randomly dropping neurons during training to prevent overfitting in the low-rank adaptation layers.
R8.
Assigns the integer value 8 to a variable named R.
Target modules, QProj, KProj, VProj, OProj, UpProj, DownProj, GateProj.
Defines a list of module names to be targeted for optimization or fine-tuning, specifically the query, key, value, and output projection layers in attention mechanisms, along with up projection, down projection, and gate projection layers commonly found in transformer architectures.
Num training GPUs 3.
Sets the number of GPUs to use for training to 3.
Num inference GPUs 1.
Sets the number of GPUs to use for inference operations to 1.
Weight decay 0.001.
Sets the weight decay hyperparameter to 0.001 for regularization during optimization, which helps prevent overfitting by penalizing large weights in the model.
Compiler equals ArborGRPO.
Creates an instance of the ArborGRPO optimizer class and assigns it to the variable compiler. This line initializes the optimizer, but doesn't show any configuration parameters or immediate execution.
Metric equals compute overall score.
Assigns the function compute overall score to the parameter metric, specifying it as the evaluation metric for the optimization process. This function will be used to measure the performance of the DSPy program during optimization.
Multitask equals true.
Sets the multitask parameter to true, enabling the DSPy optimizer to handle multiple tasks simultaneously during optimization. This allows the system to jointly optimize across different objectives or datasets in a single run.
Num DSPy examples per GRPO step equals 4.
Sets the number of DSPy examples to use per GRPO optimization step to 4.
Num samples per input equals 8.
Sets the number of samples to generate per input to 8, controlling how many variations or examples will be created for each input during the optimization process.
Exclude demos equals true.
Sets the parameter exclude demos to true, which prevents the inclusion of demonstration examples in the prompt when using DSPy optimizers. This means the system will operate without few-shot examples, relying solely on the provided instructions or zero-shot learning.
Num train steps equals 500.
Sets the number of training steps to 500 for the optimization process. This parameter controls how many iterations the optimizer will run when tuning the DSPy program.
Num threads equals 24.
Sets the number of threads to 24 for parallel execution.
UseTrain as val equals false.
Sets the UseTrain as val parameter to false, indicating that the training dataset should not be used as the validation dataset during optimization. This ensures separate datasets are maintained for training and validation purposes.
Num steps for val equals 10.
Sets the number of validation steps to 10 during optimization, controlling how frequently the optimizer evaluates performance on the validation set.
Train quargs equals train quargs.
Passes the train quargs dictionary as a keyword argument to a function or method call, forwarding any training-related configuration parameters contained within it. The exact parameters and their effects depend on what train quargs contains, but this line itself simply ensures those settings are applied during the training process.
Report train scores equals false.
Sets the report train scores parameter to false, disabling the reporting of training scores during optimization. This means the optimizer will not output or log the performance metrics calculated on the training set during its execution.
Optimized PAPILLON equals compiler compile.
Calls the compile method on a compiler object, passing no visible arguments and assigns the result to a variable named optimized Papillon. This initiates the optimization process for the Papillon system, where the compiler will tune the program's parameters such as prompts or model weights to improve performance based on predefined metrics. The output is a compiled, optimized version of the Papillon pipeline stored in optimized Papillon.
Student equals PAPILLON.
Assigns the string value, Papillon, to a variable named student. This creates a simple identifier that can be referenced elsewhere in the code to represent this specific student name.
Trainset equals trainset.
Passes the trainset variable as a keyword argument to a function or method call. This provides the training dataset that will be used by the DSPy optimizer for few-shot learning, instruction optimization, or fine-tuning, depending on the specific optimizer being configured.
Valset equals devset.
Assigns the value of devset to the variable valset, effectively using the development dataset as the validation dataset for model evaluation or optimization. The Papillon system demonstrates a privacy-preserving architecture where a trusted local model delegates tasks to an untrusted external LLM while minimizing PII leakage. The core technique involves initializing Papillon with the external model and setting the local model for inference, then optimizing the system using the ArborGRPO compiler. This compiler fine-tunes the local model's weights to maximize a composite metric that balances response quality and privacy preservation. The training configuration leverages multi-GPU training with LoRA adaptation, enabling efficient fine-tuning of specific transformer modules while keeping memory usage manageable. Parameters like gradient accumulation, learning rate, and gradient checkpointing are carefully tuned to stabilize training and prevent overfitting. The optimization process itself uses reinforcement learning with the GRPO algorithm, generating multiple samples per input and evaluating them against the composite metric. The key insight is how these components work together. The local model crafts privacy-preserving requests, the external model provides high-quality responses, and the optimization process continuously refines this interaction to improve both quality and privacy metrics. The result is a system that achieves better performance than the local model alone while maintaining strict privacy constraints, as evidenced by the 60% composite score improvement after optimization.
The model whispers LoRA config to gradient checkpointing, but forgets its own name.